The examples in the last video were all examples of ionic compounds. Now, what if you happen to be dealing with something that's covalent? Like, for instance, what if you have hydrogen gas plus chlorine gas, and that gives you 2 moles of HCl? Okay, how do you keep track of this then? So, in order to keep track of this, we use a system called oxidation numbers. And how this works is that the oxidation number is the number of charges the atom would have if the electrons were transferred completely. All right, so let me write this down. So oxidation numbers, this is the number of charges the atom would have if the electrons were transferred completely. In other words, you treat covalent compounds as if they were ionic compounds. So treat covalents as if they're ionic. Now, this really helps us identify elements that are being oxidized and reduced, because if you increase the oxidation number, then we know that the species is being oxidized. And if we decrease the oxidation number, the species is reduced. Okay, and to make a compound neutral, the oxidation numbers must add up to 0. All right. Now, there's a series of rules that we used in order to assign oxidation numbers. So I'm going to go through them. Now, the way this works is that the most common rules are up front, and then as we keep going through the set of rules, they become more and more like you're not going to use them as much. So let's tackle this. So first rule: for elements in their elemental state or free elements, each atom has an oxidation number of 0. So that means if you're dealing with something like iron, or let's say sodium, cesium, something like that, automatically their oxidation number is 0. Now, for monatomic ions, the oxidation number is equal to the charge of the ion. So if we're talking about something that's in family 1A, that means they're going to have a charge of +1. And if you're in family 2A or column 2, that's a charge of +2. Family 3A, +3. Okay. Now, if we go backwards, family 7A would have a charge of -1. Family 6A would have a charge of -2. And then family 5A would have a charge of -3. All right, so that's the second rule. Third one: oxygen usually is going to be 2-, but when you're dealing with a peroxide, like something like this, like hydrogen peroxide, oxygen carries a -1 charge. Okay. Fourth rule: the oxidation number of hydrogen is +1, except when it's bonded to a metal like this. Like, let's say you have lithium and it's bonded to a hydrogen. So you have lithium hydride. In that case, hydrogen would carry a -1 charge. All right. Rule number 5. When a halogen is combined with an oxygen, okay, they have positive oxidation numbers. So if you had something like ClO. Chlorine's going to have a positive oxidation number, not negative. All right, number 6. In a neutral molecule, the sum of the oxidation numbers of all the atoms must be 0. And in a polyatomic ion, the sum of the oxidation numbers must be equal to the net charge of the ion. Okay. And then finally, number 7, oxidation numbers don't necessarily have to be whole numbers. That is true. They don't necessarily have to be whole numbers. Now, like 98% of the time, that will definitely be true. They're going to be whole numbers. But there is that 2% where it is potential that you could have something that's like a half a charge. All right. It's very rare that we come across it, but it does happen. All right. Now, some other things that we got to take a look at. Now, metallic elements only have positive oxidation numbers. Non-metallic elements are going to have positive or negative. All right. Number 2, the highest oxidation number an element in family 1A through 7A, so any of the main group or representative elements, can have is its group number. So if you're in family 7A, the highest oxidation number you can have is +7. All right. Number 3, the transition metals usually have several possible oxidation numbers. And that's very true. So it could have a +1, +2, +3, +4, depending on what's going on. All right. Okay. So last topic we have to talk about before we leave redox reactions behind. So in a displacement reaction, we talked about if we have something like this, let's say you have compound AB and you're going to react that with element C. In order for that to happen, C has to displace A, and then A goes off by itself. So that way you get compound CB and element A by itself. Okay. So that's a displacement reaction. Now, there's 3 types of displacement reactions. First one, where you are displacing a hydrogen. Second, where you're displacing a metal. And then the third, where you're displacing a halogen. Okay, so let's talk about each of these displacement reactions one by one. So the first one is, let's say you've got a hydrogen displacement reaction. All of the alkali, or family 1A, and some of the 2A metals can displace hydrogen from cold water. So you could take calcium, okay, and that reacts with 2 moles of water. You could form calcium hydroxide, okay, and you release hydrogen gas. Now, many metals can also displace hydrogen from acids as well. So you could take something like magnesium and react it with 2 moles of HCl, and you could form magnesium chloride and release hydrogen gas at the same time. So you can displace hydrogen using family 1A or some family 2A metals. Okay. The second type of displacement that's possible is called a metal displacement. And in that, a metal in a compound has to be displaced by another metal in the elemental state. And in order to predict whether a metal will displace another metal, so in order to predict if a metal will displace another metal, we use an activity series. Okay, so what the activity series looks like is this. Okay, so we're ranking these half reactions from weakly reducing to strongly reducing reactions. And so what we're looking at is that we've got at the top, we've got an element that's breaking down to form an ion and releasing electrons at the same time. Okay, so the way this works, let's say I've got a reaction like barium, and I want to react barium with aluminum trichloride. So the way this works, we look for aluminum on the table, and here it is. I'm making a line next to it, and let's find barium. Now, since barium happens to be above aluminum on that activity series, what that means is that barium can come in and replace aluminum. Okay, but let's say instead of using barium, we decide we want to use iron. Okay, now iron on this chart ends up below aluminum. So because iron is below aluminum on this reaction, on this activity series, you would actually have no reaction. So as long as the metal of interest is higher than the original metal in the compound, you will have a displacement. If it's below, you'll have no reaction. Okay. So yeah, that's how this metal displacement works. All right. Finally, the last displacement is halogen displacement. And so the way this works is that we take a look at family 7A on the periodic table. And we have fluorine, chlorine, bromine, and iodine. So the way this works is that fluorine is going to be bigger than chlorine, chlorine's bigger than bromine, bromine's bigger than iodine. So what this means is that fluorine can displace any of the halides. Chlorine can only displace bromine or iodine. Bromine can only displace iodine, and iodine can't displace anything at all.